In this video, we will discuss the foundations of molecular rotational spectroscopy. First, looking at the electromagnetic spectrum, we will note that rotational energy level spacing is such that the spectroscopy occurs in the microwave region of the spectrum. Let's consider the rotation of a diatomic molecule in three-dimensional space. We'll first consider rotation about the x-axis. In this situation, we determine the distance of each atom from the x-axis in order to determine the moment of inertia. We'll note in this case that the distance is not equal to 0, so the moment of inertia about the x-axis is not equal to 0. Now we'll consider rotation about the y-axis. Again, we'll note that if we determine the distance from the y-axis, that it's not equal to 0. And in fact, the distance is the same as that with respect to the x-axis, and therefore the moment of inertia is not equal to 0. In fact, we'll find that the moments of inertia, because the distances are the same, the moments of inertia about the x and y axes are identical. Now we look at the moment of inertia with respect to the z-axis, and in this case we'll notice that because the diatomic molecule is in fact on the z-axis, both atoms are on the z-axis, the distance to the axis is equal to 0, and therefore the moment of inertia with respect to the z-axis is equal to 0. This is important because when we talk about the rotational energy of these molecules, we'll only have to consider the x and the y axes, for the energy of rotation about the z-axis is equal to 0. Now, as we consider the interaction of electromagnetic radiation with the molecule, we come up with the gross selection rule, which simply states that the molecule must have a permanent dipole moment in order for it to absorb electromagnetic radiation that would induce a rotational transition. We'll use the same basic equations for rotational motion that we discussed earlier, using where we have a quantum number J to determine the rotational energy. This quantum number J is the same as the quantum number L that we used in our earlier discussions and takes on values 0 and above. In rotational spectroscopy, we introduce a new constant B, which is referred to as the rotational constant, and it is always given in units of wave numbers. This just simply this simplifies the equations we'll be using in our discussion. And of course, in these equations, we'll note that I, as the moment of inertia, is equal to mu r squared, where r is the bond length of the molecule, and mu is the reduced mass. Now, in our discussion of diatomic molecules, we're considering only two axes of rotation, as we discussed earlier, and in that case, the energy level spacing, that is, the spacing between successive energy levels, which we'll refer to as J and J plus 1 here, is given by this expression here, J being, of course, the lower of the two levels. Of course, just as was the case in our earlier discussion about the quantum mechanics of rotational motion, we will have degeneracy. When we had the L quantum number, we had the M sub L quantum numbers. We're using J here, so we'll refer to these as M sub J, and M sub J, of course, represents a component of angular momentum along the z-axis. In these particular circumstances, M sub J takes on values 0, plus or minus 1, plus or minus 2, up to a maximum of plus or minus j. For any given j level, there is a degeneracy of 2j plus 1. That means there are 2j plus 1 states that have the same energy. This is actually fairly important when talking about the spectroscopy of these molecules. Of course, we already discussed the gross selection rule, which required that the molecule have a permanent dipole moment, but we also have selection rules which dictate the changes in quantum numbers that may occur when the molecule absorbs electromagnetic radiation. In this case, we can have a change in the rotational quantum number J plus or minus 1. Delta M sub J may be 0 or plus or minus 1. And this is due to the fact that the photon itself has angular momentum. It actually has a spin quantum number equal to 1. So conservation of angular momentum will dictate these selection rule rules. So looking at the transitions between successive levels, we have this table here. And we'll note that on this table, the term delta simply refers to the transition frequency of the photon involved that induces a transition for levels 0 to 1, 1 to 2, 2 to 3, etc. in these transitions. So if we look at the column here, we'll note that the frequency of the photon that would induce a transition from 0 to 1 would simply be 2 times c, being the speed of light, times the rotational constant, 4cb for 1 to 2, etc. What's interesting to note is the difference between these transition frequencies. If we look at the difference between the 0 to 1 and the 1 to 2 transitions, we find that that's 2 times c times b, which is what we have indicated here in the column on the right side. The transition between 1 and 2 and 2 to 3 is also 2cb, and we can actually see as we go down the list that the spacing is always equal to 2cb. This means if we analyze our spectra and look at the spacing between the lines in the spectra, that we can use that spacing to compute the rotational constant B. Here is a typical microwave spectrum where we see a series of spectral lines. The first line here on the left corresponds to the J equals 0 to 1 transition. Then the next one's 1 to 2. The next one's 2 to 3. The next one's 3 to 4, 5 to 6, etc. What's interesting to note is this envelope of spectral lines that we see where the maximum occurs at the transition, in this case, from level 8 to level 9. The question is, why does the maximum intensity transition occur at that particular level? To answer that question, we have to look at the Boltzmann distribution that we discussed earlier. This equation shows us the relative populations of two successive levels, level J plus 1 and level J. In that equation, we'll note that the exponential term here, the 2hcb J plus 1, is the spacing between those two levels, the energy spacing between those two levels, simply equal to that energy difference. And the terms, the G terms here, represent degeneracies. In this case, the degeneracy, you'll recall, for level J is 2J plus 1. When we figure that out for two successive levels J plus 1 and J, we end up with the expression, final expression. If we take a close look at this final equation, we'll see we can actually divide it up into two components. The degeneracy ratio in the first pre-exponential component actually will increase as J goes up. On the other hand, the exponential term, because it's e to the negative delta E over kt, will decrease as J goes up. So we have a situation where we have a mathematical function with two competing terms, one which will increase as J increases and one which will decrease as J increases. When you have a mathematical function like that, you'll find that you actually will have a maximum in that function. So if we plot this Boltzmann distribution as a function of J, we end up with these two graphs seen here. These graphs show the ratio of n sub j over n sub 0 along the vertical axis, plotted versus j along the horizontal axis. If we look at the 300K graph. That is, we plot this as a function of temperature. At 300 Kelvin, we do indeed see a maximum population. And what we'll note here as we go through this, which is fairly important, is that as the temperature increases, we will find that the maximum value of J increases. That should make sense simply because as the temperature increases, we're going to populate more molecules at the higher energy states, and we should expect that situation where the maximum J increases as the temperature increases. This ends our discussion of the fundamentals of rotational spectroscopy. We'll continue with the video on rotational vibrational spectroscopy, as well as some additional videos that deal with computations associated with these spectroscopies.